right, so section 4.3, which is our last section in chapter 4, is going to be taking a look at greatest common divisors and least common multiples. And specifically today, we're going to do the first half of that, the greatest common divisor half. So to start with, a greatest common divisor, or also known as a greatest common factor, is the greatest whole number that divides all the numbers in your set. So like that pirate example that we just did before, we weren't actually looking for greatest common divisors quite, but if we had looked at adding or subtracting different values into that list, we might have been looking for something like that. Y'all okay? Okay, good. I used this word once before. Do you remember when I used, or not word, but phrase once before, relatively prime? So relatively prime simply means two or more numbers whose greatest common divisor is 1, i.e. they have no common factors except for 1. And just as a reminder, because even if you remember me saying it, you may not be remembering where it was referenced to, it was in reference to the rule of divisibility by 6s, right? I said if we took two numbers who were relatively prime, they had no common factor except for 1, then if I multiplied them together, that list would include all the numbers that were divisible by both those numbers only, right? So that would be the only numbers that would be divisible anyway by both those numbers. So we looked at numbers like 3 and 5 worked, right? But like 5 and 10 didn't because they both have a 5 in common, things like that. All right, so there are a variety of methods for looking at and finding greatest common factors. Some of these methods will transfer over when we're looking for the least common multiples on Friday. So the first method is one that you actually saw me sort of allude to when we did the pirate example from the last section. In the intersection of sets method, we're making a list. That's the part that it has in common. We're going to make a list. What we're listing, though, instead of multiples, like I did in that problem, is we're going to list the divisors of all the divisors of those numbers. And then we're going to pick the one that's the biggest that they have in common. So here's our first example, 12 and 15. So as I'm looking at 12 and 15, what I'm going to do is I'm going to do it kind of like I did that arbor question. Do you remember Mr. Arbor where he was planting trees? And we did them in pairs to make sure we didn't miss anything. That's how I'm going to list these out as well. So one option is 1 and 12, or 2 and 6, or 3 and 4. So in my column on the right, I'm going up, in order, right? They're increasing in order. And by necessity, it means that the column on the left is going, sorry, I said it right backwards. Column on the left is increasing in the order, and the column on the right is decreasing. But I make sure that I don't miss anything by making it in an organized fashion, in whatever fashion you wish. We do the same thing with 15. I have 1 and 15. 2 doesn't work, but 3 does. So 3 and 5. And I'm done. And what I do is I consider all 6 of these numbers and all 4 of these numbers, and I ask myself, what's the biggest number that are in both categories? And it's 3. And so then the greatest common divisor, or greatest common factor if you prefer, would be 3. So you're making a big giant list. Does it make sense? It is so easy, and it's especially so easy when the numbers are small, right? If the numbers were bigger, this would be a little bit more of a problem. But we've kind of seen that before, right? Is that there's different methods that work better for different types of problems, and that's kind of the way things are. So this does work really nicely for small numbers. Yep, Hallie?
So is this also the greatest common factor as well?
Yes, exactly the same thing. So over here, when we did our definition, these two are interchangeable phrases.
Okay.
So if you want to use the word factor when I use the word divisor, fabulous, doesn't make any difference. It might even depend on, if you were teaching something with this in class, your book might focus on one of those terms over the other one, but they're exactly the same meaning.
Okay.
Yep. Okay, so then we're going to do the next one. I don't know about you, but I actually didn't, I don't remember learning this method, the one that we just did. I don't remember like listing out numbers and things like that. I'm going to guess that if it's done frequently, it's probably done at an earlier grade level, which would fit with where you guys are, or many of you at least, are planning to end up. This is the one, prime factorization, that I remember from school most commonly. So what you're going to do is first you're going to construct the prime factorization of each number. So you break it down into all of its primes, which is what we did in the last section, right? Break it down into all the primes with powers. And then what you're going to do is you're going to choose the prime factors they have in common. And then you're going to list each of those primes with the smallest exponent. Now we did something like this already. We did it when we factored numbers out in front. So I can't remember which of you had the question. I think maybe it was Grace's question. It was something at the very end anyway, where there was a number that I had and I factored out 2, but one of them had a 2 and one of them had a 2 squared, right? This is the same thing. We're looking at what they have in common. So 2, they had the number 2 in common, so I pulled it out in front. And I said, how many is the most numbers of 2s that everything has? And the most that both of them had was the number 1. So we put the number 1 as my exponent. So we list each prime with the smallest exponent in any of the factorizations. And then the last step, this is what we didn't do, step 4, was that we actually would find the product that we get from multiplying that back out. So we don't list our answer to this in a factorized form. We still multiply it back out because the original problem is usually given to us in a multiplied out type of form. So example 2, you can see I've got bigger numbers. That doesn't mean it couldn't be done with the last method that we had. It could, but it would definitely take longer, wouldn't it? It really would. Listing out all those factors would be a little bit time consuming for these numbers, partly because they're large and partly because they have lots of things that divide them. So prime factorization takes each of those numbers, and I'm going to do that division algorithm I showed you, just because we haven't seen it done quite as many times, and I'm going to divide. So 400, what's the smallest prime number that divides 400? 2, which gives me 200, which divides by 2, which gives me, which divides by, yeah, great, which divides by, or gives me 50, which divides by 2, yeah, giving me 25. No more 2s. 5s, right? 5 and 5. So if you take a look at all of the factors out here, we have 2 to the 4th, and we have 5 squared. That's the prime factorization for 400. Okay, is that okay? We're going to do the same thing with the number 360. So 360 divides by 2, leaving me with, which divides by, giving me, which divides by, giving me. Okay, so now be careful. What's the smallest prime that divides 45? It's actually 3. It's really tempting to use 5 because the end's in 5, and 3 actually works. 45 divided by 3 is 15, which divides by 3, leaving me with 5. So my prime factorization out here would give me 2 cubed times 3 squared times 5. Okay, is that okay so far? I know it feels like we've done quite a bit of work and we've only done step 1, but step 1 is the one that's the most work. Okay, so we have completed step 1. Step 2 says to choose all prime factors that are in common. So what numbers are in common here and here? 2 and 5. So these are the numbers I'm picking. Now I'm not done, but those are the bases that they have in common. Yep, Emily?
Oh, I was going to say, you put the exponents with it, right?
We need exponents with it. That's our next step.
Okay.
And we choose those exponents, if you take a look at step 3, based on the smallest power. So one of them has a 2 to the 4th, and one of them has a 2 cubed. So we use the smallest of those 2 powers, which would be then a 3. We would cube it. Yep. And then what about the 5?
Leave it.
just a 5, or if you want, you can write it as 5 to the 1 from there. Last step, step number 4, is that we're going to multiply this back out. Do you know what 2 cubed is? 8. And what's 8 times 5?
40.
40. Now, even if this might not be the biggest, you could at least make sure that it's really a factor. Does 400 divide by 40?
Yeah.
Yep. Does 360 divide by 40?
Yeah.
Yep. So at least you could make sure that you've got a factor. That does not ensure that it's the greatest common factor, but it is in fact. We did it correctly. Okay. The next method's probably my favorite. This one's the one that I am most familiar with from my learning background, but this one I did not learn until I started teaching this class, and I absolutely love it. So we'll see what you guys think. This is the division by primes method. So we write the numbers in a row, and then we have to divide each of the numbers by a common prime factor. So maybe they're both even, so you can divide them both by 2. Right? That's what you're looking for. Step 3 is that we divide the quotients by another common prime factor. And we repeat, and we repeat, and we repeat, however long it takes, until no other common factors can be found. The greatest common divisor is then the product of the primes. So what I feel like this does is it takes this process and it sort of eliminates the unnecessary parts of it that don't yield the answer to what we're looking for anyway. This is kind of an overkill. We found complete factorizations, and we didn't really need the complete factorizations, right? We just needed the parts they had in common. Agreed? So that's what this does, is it eliminates the overkill. So I'm going to do the problem with you with these 2 numbers on this particular example, but I'm going to flip back real quick so you can see what it would have looked like if I had done this with the 400 and the 360. Now I know 410 and 360 don't look all that different than the 400 and the 360, but they are a little bit different enough that you can see something. So 410 and 360, what is the smallest prime number that divides them both? It's 2. But if I divide 410 by 2, I get 205. And if I divide 360 by 10, I get 180. So they no longer both divide by 2. So I don't try that. We'll go to the next prime. Do they divide by 3? No. Do they divide by 5? Yes, they do. So what is 205 divided by 5? 41. And 180 divided by 5? 36. And we encountered the number 41 on your homework from last time, questions that when we were dividing that 32, 41 or whatever it was. 41 is a prime number. So unless 41 divides 36, which clearly it doesn't because it's bigger, we can't go any further. One's prime, one's not. So the 2 numbers that I divided by, when I multiply them back out, are my greatest common divisor. So let me show you what this one over here with those same 400 and 360 looks like in this form. So clearly we divided both by 2, had 200, 180, still divisible by 2, giving me 190, still divisible by 2, giving me 50 and 45. No longer divisible by 2, but divisible or by 3. So I divide by 5. I have 10 and I have 9. 10 and 9 clearly do not divide by anything in common. So my greatest common divisor are the 2, 2, 2, 5 on the outside. I really like division by primes because I think it's like the bare minimum necessary to get at the answer without any extra work going on, which makes it nice. Because it doesn't yield any information to us about the greatest common divisor, because it has to be a divisor in common to both 10 and 9. So while 10 divides further and 9 divides further, they don't divide further by the same values. Does that make sense?
So you can stop.
You can stop, exactly. And that's what's really nice about division by primes is it allows you to stop when there's nothing else they have in common instead of completely factoring everything out when it's yielding things you didn't really need. Okay, there's one more method. You're going to find it the most obscure. This is the Euclidean algorithm. Okay, so we're going to write it all out so you can look back and see a listing of steps to it, but it's easier to do than it is to write. We've encountered that before. We encountered it recently. Divisibility by 11 was like that. With the Euclidean algorithm, you divide the larger number by the smaller number. And then you divide the previous divisor by the remainder. You repeat step 2 until you get a remainder of 0. The last divisor is the greatest common divisor. Feels very unusual. So let me show you how it actually works. So you take the bigger number, 72, and you divide it into the larger number, 126. Okay, so always the bigger number divided by the larger number. How many times will 72 go into 126? Once. And if I subtract the 72, then 1 times 72, 72, I get 4, 5, and 54. Okay, is that okay so far? So what I do is I take, the divisor, what I divided by, and the remainder, 54. And I do the same thing again. Now the divisor, 72, is the larger number, so it goes underneath the division bar. The remainder, 54, goes on the outside. How many times will 54 go into 72? Once. Now, word of caution is not always just once. We've seen it happen once and twice, but it doesn't always give you just a 1. 72 minus 54 is 18. So we do it again with the 54 and the 18. So 54 is larger, goes underneath. 18 goes on the outside. How many times will 18 go into 54? 3 times. And that's exactly 54, leaving me with a remainder. This remainder of 0 tells me to stop. And the solution, right, the greatest common divisor is the last number I divided by. Strange, right?
Where do people find these steps?
So when you do research in mathematics, you're often looking for patterns of things that yield stuff. So this is probably someone's research in mathematics discovery along the way. So whenever you're doing research in a lot of things, we're usually not inventing things, right? We don't invent math. That is not a thing. Sometimes it feels like it. Nobody's inventing. They're discovering. They're looking for patterns in the creation that God created. I mean, like, that's it. God created it, and we're looking for patterns. And those patterns then become things that we can utilize to study math better. So let me actually do that same 400 and 360 that we had before, just so you can see this Euclidean algorithm one more time, because it's a little weird. So I'll just use the same screen that I have here. The bigger number, 400, goes underneath. My smaller 360 goes on the outside. It really does only go in once, but that's just, again, the way these particular numbers are working. I get 40 as a remainder, right? So then I'm going to look at 360 and 40. The 40 goes on the outside. The 360 goes underneath. And how many times will 40 go into 360? 9 times. This one ends very quickly with the Euclidean algorithm, right? This tells me to stop. What is my greatest common divisor? 40. It's the last number I divided by. So sometimes it works really quickly, especially if the divisors are kind of a large number. 40 is kind of a large number. If the divisors are smaller, it takes more steps to do the Euclidean algorithm before it, flushes itself out as being 2 that it all divides by or something like that at the end. Any questions about those? Okay, we will pick up on least common multiples next time.